let us solve another PDE problem. Solve one-dimensional heat equation. Yeah. So last time we solved wave equation. Wave equation, okay? Yeah. Also one-dimensional wave equation. All right. So now heat equation. So what's the heat? Slightly different. So if you compare it with the wave equation, slightly different. Yeah. All right. Here we consider a bar. Yeah, so this is a bar. The length is capital L. The location, the left end at 0, right end at x equals L, capital L. Yeah, bar under consideration. So one-dimensional heat problem. Yeah. You know, so the bar is heated, but there is some environment around this bar. Yeah. Here we skip the modeling part. Yeah. So we just get to the PDE directly. Yeah. So for the modeling part, yeah, I'm thinking about this way. Yeah. I may use the, remember we have some further explanation slots. So I may use the further explanation slots to do the modeling part. Yeah. So in our regular classes, we just solve the PDE directly. Yeah. So we can do faster. All right. Yeah. So the PDE, the form, one-dimensional form. Why one-dimensional? So you look at the right-hand side. Yeah. Here you see two variables, t variable and x variable. T variable is time variable. Yeah. When we count the number of dimensions, we do not count t variable. Okay? Yeah. Yeah. T, we always have t variable, right? Yeah. So other than the t variable, then we look at the spatial variables. Yeah. Other than t, we need to consider the spatial variables. We only have one dimension in the spatial variable part. Yeah. Similarly, for the last example, the wave. Yeah. So we also have t variable at the left-hand side. The partial derivative of with respect to t variable at the left-hand side, and with respect to the spatial variables at the right-hand side. Yeah. All right. Here you can see the main difference between heat equation and wave equation is at the left-hand side. So in our wave equation, left-hand side, it's second partial derivative, right? Yeah. So the only difference is second partial derivative. Heat equation, it's the first partial derivative. That's the main difference. Yeah. All right. Yeah. Then we need to, other than this main PDE, we also need to consider two types of conditions: boundary conditions and initial condition. Yeah, two different types of conditions in order to solve the PDE with let's say unique solution, right? Unique solution. So we need more conditions. Otherwise, you may have many solutions. Yeah. So we need more conditions in order to get one unique solution. All right. So with the c squared, the constant, with boundary condition, left end and the right end. Two boundary conditions. Left end, W of 0, t equals 0. Right right end W of L t equals 0. Yeah, simple boundary conditions. Then initial condition when t equals 0. Because t, so we consider t from 0 to infinity. 0 to infinity. Okay, all right. At a 0 point, W of x0 equals a given function, f of x. Yeah. All right. So that's the, the simplest form of the heat equation. Yeah. All right. Next, we consider a variation of this heat equation. A variation. Yeah. Slightly different version of this, typical heat equation. The difference part is at the boundary condition. Boundary condition is slightly different. Yeah. So we call this bar under diabatic conditions. Yeah. So there is a different assumption for this case. Yeah. So what's that? What is this special condition? No heat exchange with the neighborhood. Yeah. So at these two ends, no heat exchange. Yeah. But the question, so how do you describe this heat exchange with the neighborhood? Yeah. Heat exchange, okay? Yeah. So from outside environment, the higher temperature, outside the heat exchange, okay? And the inside, So that kind of exchange related to derivative. Yeah. If you have exchange, then derivative is non-zero. Yeah. Positive exchange, negative exchange, the derivative is non-zero. So for this assumption, no heat exchange, that means at both ends, the derivative equals 0. That's the different. Because here, that's the solution. The function value equals 0 for the boundary condition. And for this variation, we replace the function value at 0 by derivative. Derivative equals 0. The function value may not be 0. Yeah. The function value not necessary to be 0. So this case, we make up, the assumption here, the bar is completely insulated. Also, at the ends. Yeah. Completely insulated, including, non-end part, right? Other places also insulated. Yeah. But because here we only consider boundary condition, right? Yeah. So other places we do not consider. So here we only consider the boundary condition. So at the ends. All right. The physical information for this case, the heat flux at the ends is proportional to the wave of, So here, the rules, the rules we follow, from the physics. Heat flux, in, out, at the ends is proportional to the value of partial W over partial X. Then you can see proportional. If this value is 0, that value also 0, right? But this proportional. Because based on our example, the value at the ends may not be 0. Later, we will solve this problem. The solution, it looks like the derivative at the ends equal to 0. Yeah. But the value at the ends not equal to 0. Yeah. Well, our solution. Yeah. Yeah. So yeah. So so this physical law. Yeah. So we need to think about it. Yeah. All right. New boundary conditions. So we replace the old boundary condition by this new boundary conditions. Yeah. So the partial derivative with respect to x at two ends, left and right end, both 0. Yeah. All right. So now let us solve this special type heat equation. Okay. All right. Yeah. Now we replace. See the boundary condition. Yeah. All right. Take Laplace transform with respect to t. Yeah. So, yeah. Here you can see we do the similar thing as what we did in the wave equation, right? Yeah. We use this formula, yeah, the derivative of Laplace transform, but this time we only use the first formula. For the wave equation, we use the second formula. Yeah. So here we use the first formula. All right. Yeah. So Laplace transform. Yeah. All right. Then, yeah. F, right? So this part is known. Yeah. F function. Yeah. All right. Yeah. With respect to t. So when t equals 0, we have our initial condition. Yeah. So right hand side. Yeah. All right. Then right hand side, we do the same processing as we did in the wave equation. Yeah. Remember exchange, right? Oh, sorry, interchange between integration, and differentiation. Yeah. Integration for Laplace transform, differentiation, partial derivative. Yeah. So we let capital W Laplace transform. Yeah. So, all right. So then, S times capital W minus little f, that equals that. All right. So then this part, yeah. So we need to interchange after we interchange integration with differentiation. W get inside. Okay. Laplace transform get inside the partial derivative, second partial derivative. So capital W. Yeah? All right? Yeah. So yeah. So that interchange, yeah. So we use some assumption. We assume our solution function, W function, not too bad. Okay? Yeah. So good enough. Yeah. Yeah. So and in the real world application problems, we can easily have that assumption. Yeah. So because real world, the typical engineering problems, the solution W will not be a very bad function. Yeah. All right. So we don't worry about this interchange step. Yeah. With now, let us solve the new version, but we want to treat it as ODE. Yeah. ODE problem. Yeah. All right. So let's rewrite. Yeah. But when you see this one, rewrite. All right. So we want to find capital W, right? Yeah, we want to find capital W. Yeah. And when we find capital W, we treat this little s as a constant, fixed parameter. Yeah, it's just another constant. Yeah. So then, although partial second derivatives, but we treat as the ordinary differentiation. ordinary differentiation. Yeah? All right? Yeah? So then we have a ODE. So here we treat it as an ODE. Yeah? And only one variable x. Yeah. S, we do not treat it as a variable. It's a constant. So we solve this second order ODE. Yeah? And we know how to solve it, right? Yeah, second order ODE. You know, it's a non-homogeneous second order ODE. Yeah. Okay? Yeah. So, all right. So next, we want to solve a, concrete problem. Yeah. Yeah, because here a lot of unknown constant, right? The C constant unknown, the L constant unknown, yeah. F function not given, right? Yeah. So it is hard to do the specific calculation. Yeah. So next, we need to really solve this equation for a concrete example. Yeah. All right. Yeah. So now, this time, same problem, but we want to make C constant equals 1. Yeah. Yeah. Second, capital L. Yeah. Capital L, we make it equals pi. Yeah. All right. Then, the little f function, make it equals cosine 2x. Yeah. Yeah. Now we can solve this PDE problem. Yeah. So let's do the calculation. Yeah. All right. Solution. Yeah. Let's copy the, our new ODE. This is our new ODE. Yeah. But let's put all the known information in this ODE. Yeah. So C is gone, 1. Then F function, so we have the concrete cosine function here. So now we need to solve this ODE, second order, very simple ODE, and here we treat little s as the fixed constant. Positive fixed, and it's a positive constant. Okay, yeah? Positive constant, we can take square root. Little s. All right, yeah. How to solve this non-homogeneous second order linear ODE? Yeah. So we have the method, right? Yeah, so we have the, a standard method we can use. Yeah. Here, there is a simple case. Right hand side, little r function, right? Yeah. So first we need to identify the types of equations here. So right hand side, it is a little r function. And this little r function takes a simple basic function, cosine function. Yeah, remember, in this situation, we apply choice rules. Choice rule. Here, we use the first choice rule. A, B, C, right? Yeah. So we use the rule A. Yeah. A rule. So what's that? Yeah, because we need to represent W function in the form containing, when you see cosine, so we need to use both sine and cosine, right? Yeah, both sine and cosine. Yeah. Yeah. So we can write WP, particular. Yeah. Non-homogeneous, we need to find a particular. WH can, the homogeneous part, we can use the left-hand side of this equation, write the WH part easily, right? Yeah. So we have the confidence. Yeah. But we need to find the WP first. All right. WP A constant, B constant to be determined. But we need both cosine part and sine part. Yeah. So that's by the choice rule, rule 8, basic rule. Yeah. All right. Then, double prime, yeah, we need to, plug in into the original. Yeah. So now, we calculate the left-hand side. After simplification, you get this expression. Right-hand side, yeah, simple. So now, we need to solve this equation for capital A, capital B. Yeah. The method, very simple, right? We compare the coefficients of the corresponding terms, cosine term and a sine term. Right-hand side, no sine term, right? No sine term, that means the B is 0. Yeah? Because this B part corresponds to the coefficient of the right-hand side. So you can see the comparison that B term is gone. So only A terms left, but we can find the A term easily. Yeah. Negative, both sides cancel out. So capital A equals 1 over S plus 4. B equals 0. Yeah? So WP is found. Yeah. Let's write WH. Yeah? WH. Yeah? Characteristic equation lambda 1, lambda 2, right? Yeah. All right. Yeah. So WP is known. Yeah. Next, we need to write WH. Yeah. All right. Yeah. So we look at the homogeneous version of the original equation and consider characteristic equation. Lambda squared minus positive number S equals 0. So we have lambda 1, lambda 2. Yeah. All right. Yeah. Then let's write the general solution. WH, C1 times, yeah, and C2 times, yeah, yeah. These two functions. Yeah. All right. Then, now we can write capital W X S, the general part, H part, and P part. Yeah. P part. All right? Yeah. C1, C2, unknown. But C1, C2, can we use the, given condition, right? Yeah. Initial. We need to use the boundary conditions. These two boundary conditions to determine C1, C2. Yeah. Left and right end to determine C1, C2. Yeah. Yeah. Initial condition, this one, we already use it. Yeah. So in this case, yeah, we cannot use this. Yeah. It does not help. Okay? Yeah, but we need to use the two boundary conditions. All right. So now let's take Laplace transform. Yeah. So I mean capital W. We need to get to the capital W. Its definition again. Yeah. So here. Yeah. Right. So capital W. Yeah. So here. All right. Yeah. Because based on this form, we can calculate partial capital W over partial X. Yeah. All right. Yeah. Because the boundary condition, we need to take partial derivative, right? Yeah. The boundary condition, we need to take a partial derivative with respect to X. So that's why here, we also need to take partial derivative on capital W with respect to X. The difference is here the given condition is a little w partial derivative with respect to x. Here it's a capital W with respect to x. That's the only difference. That difference, we can take Laplace transform to connect them. Yeah. So now we apply the, interchange, differentiation, and integration. Yeah. Again, yeah. So here, let's apply Laplace transform both sides. Right? Right hand side 0. Yeah. So left hand side related to capital W. Right? Yeah. All right. Left hand side, let's take interchange. Interchange, right? Yeah. So here I skip that Laplace step because that step is very simple, straightforward. So Laplace, left hand side, right hand side also Laplace of transform of 0, also 0, right? Yeah. So also 0. Okay? Yeah, same 0. But this one we can do interchange, right? Integral and differentiation. Right? Yeah. So when we do that interchange, we move the Laplace transform inside differentiation. Inside, so you get a capital W. Yeah, inside you get capital W. Yeah. So use that assumption. Yeah. All right. So then, what you have this for, can you plug in? Yeah. So the upper equation, you can plug in when x equals 0. Plug in. Okay. Plug in. So you get one equation related to C1, C2. Yeah. So you get the first equation for C1, C2. So the difference of these two constants equals 0. They are the same. Yeah. But we need a second equation. And L is pi, right end. Pi. Do the same thing, but at a pi. Okay? All right. Yeah. So take Laplace transform for the right end boundary condition. Yeah. So we get this case. So we plug in pi. Yeah. So x equals pi. Yeah. The sign term also gone. So pi, right? Yeah. So this time we get the second equation. Yeah. We use these two equations, we can find C1, C2. Yeah. C1, can you see C1, C2 equals 0? Yeah. Because C1 equals C2. So C1, C2 the same, but their coefficient is different, right? Yeah. Yeah, coefficient is different. Yeah. So if you just factor out C1 times e to the pi root s minus negative pi root s, we know s is greater than 0. Yeah. Yeah. When we do Laplace transform, we have this assumption. Then, so this parenthesis part is non-zero. Yeah? Yeah. Non-zero, then the only way we can get this equation is C1 must be 0. So C1, C2 must both 0. Then this part is gone. Right? Yeah. So we only have the last term. So the final solution, W, capital W function, is this concrete function. Yeah. No constant. Yeah. But we need, our goal, we want to find little w. So we need to take inverse Laplace transform on capital W. Yeah. But with respect to s, right? Yeah. We treat x as constant. We treat x as constant. So we apply, on the s part, s plus 4, first shifting theorem, right? First shifting theorem. Yeah. All right. So the solution, yeah, because inverse Laplace transform equals 1, right? Yeah. So let's recall inverse Laplace transform of 1 over s equals 1. Okay? Yeah. Then the shifting part plus 4, you need to multiply that 1 by e function, right? Yeah, certain e function. Yeah. Yeah. All right? Yeah. So e to the negative 4t. Yeah. Yeah. So that's the t part. Yeah. Cosine x part, x constant. So you treat cosine of 2x, it's a constant. Yeah. So you just copy the constant part. Yeah. So now you can see the final solution is this function. So we find a final solution. Yeah. You can go back to the original equation, verify it. Yeah. It satisfies the original PDE with the given conditions. Original PDE, very easy to see, right? Yeah. The partial derivative with respect to negative 4 out. Then partial derivative twice on x, you have negative sign, right? Cosine, sine. So back to cosine function and 4. Yeah, because chain rule, 2 times 2, 4. Yeah. So satisfy the original equation. Then you check the condition, boundary conditions, partial derivative with respect to x, you get a cosine 2x, right? Yeah, 2 times negatives, 2 times sine. Sine 2x at these 2 points, both 0. Yeah, left hand. Sine 2 pi 0. Sine 0 also 0. Yeah, so this boundary condition is satisfied. Then initial condition, when t equals 0, you have cosine of 2x. So all the conditions are satisfied. Yeah, so that's the solution. Yeah. Yeah. All right. So we have seen 2 relatively simple examples. Although you need to do a lot of work, right? Yeah. But for PDE, solving PDE, so these 2 examples, relatively simple. Yeah. So not too hard. Yeah. Yeah. So for this class, you need to be able to solve equations, yeah, like these 2 examples. So wave equation and heat equation, yeah, and with different coefficients and different boundary initial conditions. No? So then, so you have this part, yeah, because later we have other techniques. Yeah. Later we need to learn other techniques. Yeah. Yeah. Fourier transform. Yeah. 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 But before the midterm, yeah, so that's all we need. Yeah. For PDE part. Yeah. All right. Yeah. So that's part F. Yeah. Next, we need to go back to part E to complete the last topic. Yeah, so last topic, modeling, electric circuit. Yeah, solution by variation parameters. Yeah, so we review a little bit. Okay, yeah. So we do the one application problem in electric circuit. Yeah. All right. Yeah. Hope before the break we complete this last topic. So then we can start module 3 after the break. Yeah. Remember last time, yeah, So remember the last class, after we derived the second shifting theorem, and we did one application problem in electric circuit, there is a Q function, right? Yeah. When we apply Laplace transform, the Q function. Yeah. So here in this part, yeah. So we will, look at the physical laws on that part. Yeah, because the Q function, I didn't mention any physical laws, right? Just give you. I told you that Q is the integral of I function. Yeah. Here we look at that part. Yeah. All right. First, let's look at the formulas in electric circuit. Yeah. So we have learned several formulas before, yeah, but here we need to learn some new formulas. Right. Yeah. So we consider, yeah. So three types components: R, C, L, or RLC, Yeah. 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 So these rules, yeah, actually these rules we have learned before, right? Yeah. These, yeah. At least the first two rules we learned. Laws we learned before. Yeah. Yeah. So then C, yeah. So there is a Q function, amount of electric charge stored in the capacitor. Yeah. Yeah. All right. So then we need to learn, yeah, the relationship between current I and Q is this. Yeah. Yeah. I equals derivative of Q with respect to T. Yeah. And also, yeah, we can write Q as the integral of I function. Yeah. So that's the one last time we use it. Yeah. And here we still use the capital notations, but because this place, people using these notations because they do not have the Laplace transform in their mind. Yeah. Yeah, so they just, choose, reasonable notations. But when we go to the Laplace transform, then people want to change. Yeah? Because capital letters represent Laplace transform, right? Yeah, not the original functions. So that's why when we need to apply Laplace transform, we need to use the convention. Yeah, here it's the convention. Okay, the convention is the original functions before the Laplace transform. We use the lower cases, little I, little q. Yeah, so people know. So these functions, original functions before we apply Laplace transform, then the uppercase symbols for the Laplace transform of the corresponding functions. Yeah, so that's very convenient. Yeah, yeah, but here, yeah, people do not have Laplace transform in their mind, so you see the capital letters. All right, then Kirchhoff's voltage law. Yeah, voltage drop. Yeah, so we saw this before. Okay, yeah, equating the voltage drops across the resistor and the inductor and the capacitor to the EMF, electromotive force. Yeah? Electromotive force, this E function, equals voltage drop. You accumulate the voltage drops through all the components in this electric circuit. Yeah? Pretty straightforward. So if we write specific equation, so that's the, whole equation. Yeah. Left-hand side, 3 terms, I prime r times I, but there is an integral. Yeah. So if you look at the structure here, although there is an integral, yeah, but you can see if we, because this integral is a Q function, right? Yeah, Q function. Q function over C. Yeah. Then that I is the Q prime, right? Yeah. I is the Q prime. And then I prime, that's the Q double prime. Okay? Yeah. So if you look at it in that way, this is the second order ODE. Second order ODE, yeah. Yeah. Although, yeah, you see some integral, yeah, both integral and a derivative, yeah, but the essential structure, second order ODE. Yeah. Yeah. All right. That, so we have confidence because we know how to solve this type of equations. Yeah. All right. Yeah. But there is another way. Yeah. So here, there are 2 ways. The first way, we can write the corresponding version with respect to Q function. Yeah. So that's one way to solve this ODE. But there is another way. Yeah. Also, frequently used is this way. We take a derivative both sides. How about that? Yeah? Because this equation, always true. So we can take derivative both sides. Yeah. If we take both sides, we get another second order ODE. So L times I double prime plus R times I prime plus, yeah? So integral, we apply the fundamental theorem of calculus. So we get I, right? So derivative of this integral, yeah, so we get I. Then E prime derivative, we can find, by chain rule, we can find it E prime function easily. Yeah? And you can also solve this, the second version. 2 versions. Yeah. Yeah. All right. Yeah. So here, right. So look at the 2 versions, right? Another version is the Q version. So you have the Q version, you have the R version. But they are equivalent. Yeah. These 2 versions equivalent. Yeah. Both second order ODE. Yeah. Yeah. Okay. Yeah. All right. Now let's solve a simple application problem. Yeah. RLC circuit. Yeah. Yeah. So here we just get the specific numbers. R number, L number, C number, and the E function. Yeah. Specific E function number. Okay? All right. Yeah. Yeah. So then, also initial condition. Assume that the current and capacitor charge are 0, where initial condition, when t equals 0, yeah, initial value of I function and the Q function, both 0. So then we can find the, a fixed solution. Yeah. 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 So let's work on the I version ODE first. Yeah. Yeah. And here we do not plan to take Laplace transform. So here we use our, previous technology. Yeah. And yeah, non-homogeneous. All right. Yeah. But form of the r function, little r function, yeah, cosine function. So we need to calculate IP, right? Yeah, P. P should have both sine, cosine. Yeah, yeah. So here we, use the specific constant. Yeah. All right. That simplification. Yeah. So the the characteristic function of the homogeneous. Yeah. Yeah. So then, yeah, we get two solutions. Yeah. So we can write IH first easily. Yeah. IH. Yeah. Yeah. C1, C2. Yeah. Yeah. Later we will use the two initial conditions to find C1, C2. Yeah. Next, we need to write IP in the form A with A constant, B constant to be determined. Yeah. Yeah. Plug in, so we try to find AB constant. Yeah. Yeah, so here, yeah, because when we do the calculation, so the form of so many different constants, combined in a relatively complicated way. So in order to simplify the form representation, so some special concept is introduced. Yeah. So there's reactance is defined as capital S equals omega. Yeah. Here, well, omega. We have omega, right? So the omega given, right? This 377. Yeah. So this number, 60 times 2 pi. That's omega. Okay. So we introduce a new concept, which is a constant capital S defined by omega L minus 1 over omega capital C. Yeah. Because this special constant will be used in our final solution. Yeah. So we want to make our final solution look simpler. Yeah. So we use this constant. So let's calculate that capital S. Based on the given data, so we get, approximately that number. Then we represent our solution. Yeah. So based on the calculation, we plug in, yeah. When we do the calculation, we still use L, R, C. Yeah. So now because we want to derive the general formula. Okay. General formula for little a and the general formula for little b. Yeah. And so here, so after our calculation with the symbols, we get these two formulas. Yeah. For the little ab. Yeah. So later you can plug in. Yeah. With the form. So you do not need to go through all the details. Yeah. Later, so in this situation, you can calculate little a, little b, yeah, but you need to calculate capital S first. Yeah. So then, yeah. So E0, you have E0, right? Yeah. E0. You also have E0, the coefficient. Yeah. Right. Yeah. So we didn't mention E0. Yeah. But you look at the form here. So you know the E0, right? Yeah. So why? Yeah, because E0, the leading coefficient of that sine function. Yeah, so that's this, 110. Yeah. So you have that E0. Yeah. Yeah. So you plug in. Yeah. So you can find the value of little a, little b. Yeah. So then you have IP function. Yeah. Yeah. Then we need to determine C1, C2. Yeah. C1, C2. So two initial conditions. Yeah. All right. Yeah. Yeah. So here I didn't complete the remaining part. Remaining part not very hard, right? Yeah. Remaining hard. Yeah, because IH plus IP, but you need to plug in t equals 0. Yeah. So here, yeah, because we have a few minutes before the break. So I just write a few steps, yeah. Although pretty easy, straightforward. Yeah. But we just want to see how hard it is. Yeah. All right. Because we need to calculate IH of 0 at t equals 0 plus IP of 0, that's I of 0 equals 0. That's the first equation. Okay, all right. So IH 0, 0 gone, so C1 plus C2, IP 0, 0, that's little a, right? Yeah. Plus A. A is known, so first equation. Second equation, Q, yeah, Q so how to use Q? How to use Q? Because here, how to connect to Q, right? Yeah. And we can find C1 plus C2, some value, negative A, but that's not enough to determine C1, C2. Yeah, so here, yeah, based on this example, we can see something. Yeah, because although we have the Q condition, but it's not easy to apply it, right? How to apply it? Yeah. So that's something not convenient, right? Yeah. Think about that. Yeah. So here, using this example, yeah. So that tells us something. Tells us something. Yeah. How to get around the situation. Yeah. Because at the end, we need to determine little c1, c2. Yeah. So we need one more equation about c1, c2 to find final solution. Yeah. So think about, under this situation, what should we do? Yeah. So it's at a break time. Yeah. So let me just raise the question. After you come back, then I talk about. Yeah. So we need to find a way to get around this problem. Yeah. All right. So after 7:10, yeah, a little bit. So we continue. Yeah.